Hey everyone. So we looked at the two main forms, really the only two forms of L'Hopital's rule. When we've got the quotient of functions, right, the limit of a quotient of functions, if both functions go to zero or both functions go to infinity, plus or minus infinity, doesn't matter, then we can take the limit of their quotient by taking the limit of the quotient of their derivatives. And sometimes this is easier to do or possible to do, right? Because those indeterminate forms, 0 over 0, infinity over infinity, don't tell us anything on their own. And so if one of our earlier methods, doing some algebraic manipulation or something like that, if those aren't available, L'Hopital's rule, and even if they are, sometimes L'Hopital's rule is just a simpler method for doing these. So we're going to look at, I'm calling it other forms, but really all we're looking at is, what if the thing you're looking at doesn't fit into one of these? Can you ever use L'Hopital's rule? And the answer is you can if you can make it fit into one of these forms. So let's do an example to make clear what I'm saying. If I look at the limit as x goes to 0 of x times the natural log of x, right? My limit laws tell me I can look at, excuse me, these two limits, their product. Well, as 0, x goes to 0, x goes to 0. So this first limit is 0. The problem is this second limit, as x goes to 0, the natural log of x, we should be, pardon me, we should be approaching from above because it's implied because of the natural log. Let's make it explicit. The natural log can only take, right, values from above. As we approach 0 from above, from the right, natural log just keeps getting more and more negative. This limit is negative infinity, right? So we've got 0 times an infinity, right? One's trying to make things small, one's trying to make things big. And we don't know who wins, right? There's nothing about this as written that tells us who wins. So what we need to do is we can use L'Hopital's rule. But the way we use it, because we need to fit into one of the rules I have sketched out above, is that we're going to do a little bit of clever algebra and rewrite this like this, right? I've only used algebra here. The only piece of calculus I'm really using here is the fact that these two things are only equivalent when x is not equal to 0. But as we remember from limits, the limit as x goes to 0 doesn't care about what happens at 0. So all the places this cares about, these two formulations of our function, x times natural log of x and natural log of x over 1 over x, are the same, right? So I've written it in this interesting way. And the reason is because now we already remember that the natural log goes to negative infinity. As we approach 0 from the positive side, 1 over x goes to positive infinity. So now we have this infinite case of L'Hopital's rule. So I can take derivatives of the numerator and the denominator functions. The derivative of natural log of x is 1 over x. The derivative of 1 over x is going to be negative 1 over x squared. And now I just do some algebra. So I've got negative 1 over x times x squared over 1, which is just the limit as x goes to 0 from above of negative x, which is, of course, 0, right? As x gets closer to 0, so does negative x. Okay, so we saw who won that fight. In this case, the 0 did, but it didn't have to be that way. There are plenty of examples where the opposite happens. Okay, let's look at another odd sort of case. Suppose we wanted to understand what happens to this strange function, x raised to a power of 1 over itself. What happens as x gets large? Well, two things are happening. The x as the base of this exponential function it's not really an exponential function, but x as the base to this exponent is getting larger. When you have a larger base, the overall expression gets larger, right? Regardless of the power you raise it to, except the power here is changing. And so as we make x bigger, we make the power smaller. The power is getting closer to 0, and numbers taken to the 0 power are always 1. So that exponent is trying to make this thing a 1. The base is trying to make this thing infinite, right? In other words, if I was going to write something highly inappropriate, it's as if I'm trying to figure out what's infinity to the 0 power, right? That 0 power wants me to have a 1, infinity wants me to have infinite, and it's not clear who's winning, okay? So here's what we're going to do. We're going to note that x to the 1 over x is equal to e to the natural log of x to the 1 over x, right? That's just how the exponential and the logarithm works, right? They're inverse functions to each other. We don't have to worry about positives. We're taking x to be out to infinity, so there's nothing around that we have to worry about. We're also going to apply a property of logarithms that lets us take this exponent out to the front. So we're going to replace our expression with e to the 1 over x natural log of x. Okay. The next thing I'm going to use is the fact that if I have the limit as x goes to infinity of f of g of x, this is the same as the limit f of the limit as x goes to infinity of g of x. As long as these two functions, so g, the outputs of g have to be in the domain of f, and f has to be continuous. We've got all the stuff we need for that here, okay? So in this case, in particular, I'm looking at e. E is my function, and I'm going to take the limit into the exponent. The g of x will be that thing that we have up here. Okay, so my next line is to write this as e to the limit as x goes to infinity of 1 over x natural log of x. So now let's take this exponent and just do some work on it. The limit as x goes to infinity of the natural log of x over x, right? 1 over x times natural log of x is natural log of x over x. This is a perfect case for L'Hopital's rule because both of these things go to infinity in the limit. The limit as x goes to infinity of natural log is infinity. The limit as x goes to infinity of x is infinity. So we can apply L'Hopital's rule. We have the limit as x goes to infinity of 1 over x over 1, taking those derivatives. So of course, nothing happens to the denominator as x goes to infinity, but 1 over x goes to 0. And we have our limit is 0. That's not the limit to finish the problem. That's the limit of what we have going on in the exponent. So we now can replace that limit with 0, and we get 1. And so the fight appears to be won by that exponent. It's making sure this thing doesn't grow very fast. It stays as numbers close to 1, right? We don't actually get there. This limit doesn't tell us that we're going to ever be equal to 1, but it keeps getting closer and closer to 1. All right, let's do one more example. I think that'll be good. Another kind of indeterminate form. The limit as x goes to pi over 2 from below of the secant of x minus the tangent of x. Okay. Well, let's just take a quick look. Try to remember these graphs. If we look at pi over 2, so I'll call this x equals pi over 2. Tangent, we know, has an asymptote like this, right? We're talking about approaching pi over 2 from below, so I don't care what happens on the other side. Secant also has an asymptote there. All right, so they're both going off towards infinity, which means that the result of this limit is the nonsense infinity minus infinity, right? This is indeterminate. We don't know. This is not zero, right? Or it could be zero, but it could also be infinite. It could be negative infinity, and it could be a number in between those two. We don't know what it is, okay? So we have to do some work to see what it might be. So what we're going to do is rewrite these using their definitions. All right, so I can say that secant is 1 over cosine of x. And then tangent is sine of x over cosine of x. And then I've got fraction 1 minus sine of x over cosine of x. Now, what we need to notice is that the derivatives, the limit in the numerator and the denominator are both 0. Sine of pi over 2 is 1, so we have 1 minus 1 is 0. Cosine of pi over 2 is 0, so we have 0 over 0. This is a candidate for L'Hopital's rule. Take the derivative of the top, I get negative cosine of x. In the denominator, I get negative sine of x. And now I can take this limit. Cosine of pi over 2 is 0, sine of pi over 2 is 1, and so we end up with a limit of 0. So in this case, it happened to be 0, but it did not have to be. That way. Okay, that is it for now. Thanks everybody. I will see you next time.